record. Okay. And let's see. I see 3 chats already. Good morning, all. Malayo ko ice cream na. Okay. Right there, next to you. I'm sharing it to everyone. Virtual ice cream on your way. There you go. All right, well, welcome everyone. This is our last week. I am so excited. So let's make sure that, let's just go back to the assumption of structural equation modeling. Just a recap again. Structural equation modeling is a very complex and very advanced statistical and analytic procedure. And it combines not just one analytic approach, but almost like 3 or 4 different analytic approach and simultaneously put in together. An example of that is that there is linear structural relationship that's being used, and that's why the first software that can actually perform structural equation modeling was named LISREL, L-I-S-R-E-L, because it stands for linear structural relations. And that's one of the assumptions of structural equation modeling, that it uses linear regressions. And the other analytical procedure that's being utilized simultaneously by SEM is the path analysis, which definitely look at cause and effect, and not just relationship by association, but it's really a cause and effect relationship between variables. And then SEM, or structural equation modeling, also uses maximum likelihood estimation. So you could just see how complex this this model, or this statistics, structural equation modeling. And there are mathematically, there are very strict rules on how the variables are plugged in and utilized, or I would say applied to specific areas in the software. SPSS right now actually don't have structural equation modeling. You can have AMOS and you can have STATA, and they can perform structural equation modeling, but SPSS actually has not incorporated SEM into one of their analyze function. So I'd just like to re-emphasize again that structural equation modeling is a combination of multiple analytic procedure that includes linear regression, linear structural relationship, your maximum likelihood estimation, and then it also utilized path analysis, and then it does this simultaneously, and all the math are put into the software, and it's the first software that was able to perform all of this simultaneous function is called LISREL. So with that being said, I'd like us to continue from last week, and we're going to look at the SEM assumptions, or structural equation assumptions. So there are 3 types of assumptions that must be considered with SEM, and that is the theoretical, the general statistical, and the estimation method specific. So the first one, the theoretical assumption, that is where your hypothesized relationship with the construct are being tested. Then you have the general statistical assumptions, where that's where the linear structural relationships are being tested. And then that's where also the maximum likelihood estimation and then the path analysis mathematical underpinnings as well are being incorporated. And then you have your estimation method specific statistical assumption, where it's measurement specific. This is now looking at the measurement model, and that is examining how those theoretical constructs are being measured. So very technical. So you have your theoretical model and you have your measurement model in very distinct definition. The measurement model is the model of how theoretical constructs are measured. So that's why it's called measurement model. And then the theoretical model is a model of the hypothesized relationship of the construct. So this is this approach, this structural equation modeling, allows us to ask questions in many different ways as a researcher. It gives us a lot of new ways or new lens to examine how phenomenon really is, how phenomena or phenomenon is or are happening in real world. And so this is a very exciting time when I was actually in grad school, when SEM was introduced, and there were a lot of PhDs who were very interested in SEM. And I'm planning, I actually, because I submitted my abstract for my initial proposal for my PhD to one of the journals, the Communication and Nursing Research, but that was old, so I have to get it to the library through interlibrary loans. As soon as I get a copy of my own work that I submitted, I will send it to you, and it really shows how complex initially I thought decision-making in cancer patients is all about. And I really thought that SEM would be the appropriate way to examine the phenomena of interest that I was very interested in when I was doing my PhD. So I will send that to you as sort of like to give you more flavor of where, when, and where to use SEM when you are investigating a phenomenon. So the theoretical assumptions is, again, assumptions of causation are made regarding both measurement of the latent variables and the relationship between latent variables. And these assumptions are made when paths are drawn or parameters does not equal 0, or when the paths are not drawn, and that is when parameters equals 0. And in SEM, the way how we use arrows, whether it's unidirectional or bidirectional, when we use circle, is it a big circle? Is it a small circle? Is it a rectangular shape or a square? They actually have mathematical meaning in structural equation modeling, and I will show that to you in one of the publications. So just like path analysis, SEM, it's important that there are 3 conditions of causation, because SEM utilizes path analysis as one of its properties. As I mentioned earlier, SEM utilizes multiple analytical procedures, multivariate analysis, covariance analysis, linear structural relationship, maximum likelihood estimation. This is like an amazing type of advanced statistics. It really is putting all the, I would say, the whistles and that's what they say, this is the most sophisticated type of statistical analysis in social science. And so going back to this, that when we think of cause and effect, there has to be three conditions that must be met. And that's the first one, is that the presence of observed and measurable relationship between the variables. Number two is temporal ordering, which means time, which means that if it happens at 9 o'clock, then it leads to an event at 12 o'clock. So there is that time ordering. Or as I mentioned last week, temporal means really that there is a prerequisite. So one has to happen, A has to happen before B will happen, and B has to happen before C will happen. So that's an important component of cause and effect. Just like when you do experimentation, when you put sodium to chloride, then it becomes sodium chloride, and that, if there are any timing that's involved in that, then that is one of the important components, is the temporal ordering. What is the timing? What is the distance of the timing? Does it take at least 6 hours before B will happen? Or does it require 12 hours after A had happened before B will happen? So that is what we call temporal ordering. And that is one of the requirements of cause and effect, or what we call causation in scientific inquiry. The last component of the cause and effect is the non-spuriousness, or simply put, it's not fake, that it is the reality. It is not subject by chance. It is not random, and that there are no manipulations of the other potential factors that could lead to a spurious result, or what we call a fake result. So these are really very, very important conditions of cause and effect. And that is an assumption that is listed in, that is one of the assumption of SEM. So the general statistical assumptions, three types. You have your linear regression, that it has to be normally distributed, that there has to be homoscedasticity, or the homogeneity of the variance, and that there is linear relationship. And because SEM is literally a covariance, it's a covariance structure modeling, sort of, that's the other name of SEM, is a covariance structure modeling. It does look at the linear relationship. And then the assumptions regarding the error terms in SEM is similar to those for regression, which means that the error terms in the model are not correlated with any latent variables, that they are independent of one another, and that they are normally distributed. And then the last general statistical assumption, of course, is that the sample is asymptotic, that they are large enough to almost approach infinity. So as I mentioned, that this SEM also has a component of maximum likelihood, and that is the estimation method specific statistical assumption of SEM. And so in addition to general statistical assumptions, such as those linear structural relationship, you also have this assumption that's incorporated into SEM, which is the distributional assumptions are associated with the maximum likelihood. It simply means that it is using the parameters where you get the maximum likelihood to fit the model, or what we call the goodness of model fit. Maximum likelihood assumes that no single variable or group variable perfectly explains another. That's why there's iteration in maximum likelihood, because of this critical underpinnings of maximum likelihood that says that there's no single variable or group of variables that perfectly explains another. And that's why this is called as a covariant structural modeling, because the assumption of SEM is that there's no single variable. So that's where it gets its synonym of covariant structure modeling. So in the textbook, in Monroe's statistical health research method textbook, what they have shown is an example of a theoretical model of condom use for African-American men with a partner they know very well. And then in the example in the textbook, they look at SEM to determine which parameters are significant and whether the model as a whole provides a good fit to the data. So they have their hypothesized model, and that is what you call the theoretical model. And then they also have their measurement model, which is basically the model where the theoretical construct are being measured. So this is the initial theoretical model of the sample in the textbook. And as I mentioned earlier, that if you have bidirectional arrows, you can see that some of these arrows, they are bidirectional. That actually means association. And whereas the arrow that's unidirectional, the one that is pointing only in one direction, that is actually showing cause and effect relationship. It has a direct effect to the latent variable. And the latent variable are the ones that are in circles. So these are the hypothesized latent variables in this example in a textbook where it examines the factors of condom use in HIV patients who has a partner that they know very well. So the hypothesized constructs are interpersonal consequences, AIDS communication, whether their partner is open and honest about their AIDS status, their AIDS concern, embarrassing, pleasure, condom predisposition, condom use, and alcohol use. So there are 8 latent variables here, and they put age in a square because in structural equation modeling, it actually has a mathematical meaning. So in the SEM example, the theoretical model contains 8 latent variables, and I've mentioned them already, interpersonal consequences and so on and so forth. And age is included, and it's specifically demarcated with a square because it has only one indicator and it is assumed to be measured without error. So that is emphasized here in this slide set because it has a mathematical implications when they program LISREL they actually have very specific mathematics on how to account for variables that are not subject to measurement error, whereas other variables are definitely subject to measurement error. So you have your error term, and again, the way how the theoretical model is actually presented has a lot of implication on how this values of variables will be plugged in into the less real program. So I've sent you 2 readings about SEM, and I think those are the best one that I could share to you. It really, those 2 are really enhancement readings for those who want to use SEM in your doctoral dissertation. I think that those 2 articles that I sent you should be your Bible, because it's quite comprehensive and very explicit about what every circle and square and arrows and symbols means mathematically by the time this variables are already measured, and by the time you plug in all the values into the LISREL program. So the measurement model for the latent variables fit the data well is another assumption, and that's the example in the textbook. And then separate measurement models were tested for each latent variable. And then the CFIs, those that were 0.91 or more, and the relative chi-squares that range from 0.2 to 1.80 are what we call plugged in into the measurement model. So in the example in the textbook, the computer output from this showed that the model was empirically under-identified when it is estimated and was tested. But then it was over-identified by constraining the error associated with condom predisposition to be equal to 0. So this is something that's very abstract right now, because I have to keep going back to the textbook and really look at what they meant by this. And so I think that the articles are much better reading for all of you, because you have all the important information there, and you actually have a little bit of problem with access to the textbook. So I highly recommend that you do an enhancement reading using those PDF articles, because right now what the slides is saying is quite abstract, looking at condom predisposition as equal to 0, and it has a lot of pre-reading before you will be able to understand what this statement is all about. And then the final statement here in the slide says that the computer's choice of this particular constraint suggests there are too many latent variables diagrammed as influencing the condom predisposition. So they have to look for sort of a lesser number of latent variables plugged into the model in order to fit the entire data and to have a better fit of the model. So lo and behold, this is the reason why they explain those things, because now they are showing us a sort of this is the first re-specified model. So they have removed some of the components and some of the different relationship and the different direct effect of one variable to the next variable. So this is the first re-specified model. Sort of like, I have to go back here, look at how this first initial theoretical model, and look at how many arrows, and some are bidirectional and some are unidirectional. And if you look at age alone, it has 3 additional arrows that's pointing down. You probably wonder, where is that arrow going? Why is it going somewhere where there's no variables being identified? Well, that's actually indicating something what we call the residuals in our linear regression modeling. So this is the initial theoretical model, and if you look at that, it has a lot of this relationships, and as well as cause and effect assumption in the initial theoretical model. But if we look at the first specified model, it looks cleaner, a little bit nicer to the eyes, and it removes some of the arrows which claim to be having a direct effect on the condom predisposition, because the 2 main latent variable here, so I forgot to mention this, that the one on the right side of the slides are the outcome variable. So that really, that's very important. That is the phenomenon of interest here, is the condom use and the condom predisposition. And then you have many variables that are probably are associated with each other, or has a direct causal relationship to one of the variables. And so in this first re-specified model, you will see that there are less bidirectional arrows, which means that there are less associations between variables in order to have a good fit to the model. And then the cause and effect as well, and the residuals are lesser. So this gives you a flavor of how structural equation modeling is. And I think my goal is just to give you sort of an introduction to structural equation modeling. And you will really need to spend a lot of time and a lot of you need a lot of mentoring from someone who uses SEM as their primary way of scientific inquiry, and that's where you get the most of SEM, is really to have practice and also models. So in continuation with the example in the textbook, the fit of this new model is acceptable. The CFI equals to 0.90, so that is sort of the cutoff. And then given acceptable model fit statistics, now we want to know whether the re-specified theoretical model are necessary. Would dropping any of the parameter represent this path significantly also affect the fit of the model? And then they also will continue to do additional tests, such as the Wald test. And the Wald test will look at 3 paths that could be dropped. from age to alcohol use, from alcohol use to condom use, and from AIDS concern to condom use. So let's look at this. So let's alcohol use to condom use, the AIDS concern to condom use. And so this is where the Wald's model is basically looking at dropping the three paths. It's age to alcohol use, and then alcohol use to condom use, and then AIDS concern. So here's your AIDS concern that goes to alcohol use. They remove it because AIDS concern to alcohol use to condom use, and then age to alcohol use, and then condom use has been removed by the Wald's model. So this is now the second re-specified model in the structural equation modeling. So this, again, I just wanted to give you a flavor of what structural equation modeling is. So because it looks at a measurement model, it looks at theoretical model, it does have this initial theoretical model followed by the first re-specified model, and then followed by the second re-specified model. So there's a lot of steps in structural equation modeling. And then the bottom line is it's looking for the best fit of the data to your theoretical model, which is your hypothesized relationship of your latent constructs. So again, this is the last slides. There are possible type 2 error, which means that you are actually incorrectly retaining a false null hypothesis. This is what we call the false negative, because the type 1 error is what we call the false positive, where we reject the null hypothesis, but actually we do not have a statistical significance. But here in SEM, there is really a danger for type 2 error, and that is incorrectly retaining a false null hypothesis, also known as false negative. So that's one of the limitations of structural equation modeling. And then in this data set, they said that the limitation is that this is a cross-sectional. So cross-sectional design will never give you cause and effect relationship. Cause and effect means remember one of the conditions of causation is temporal ordering. So if your design of your research is cross-sectional, you only have a snapshot at a certain point of time, then there is no temporal ordering. And so in order for this theoretical relationship to become validated, you need a longitudinal study. All right, so any questions right now before we take our 15-minute break? All right, well, it's 8:42. How about if we reconvene in 18 minutes? So that's about 9 p.m. my time. All right, class. See you in about 18 minutes.